Okay, good afternoon. We are looking at operation research, and this course has a number of topics, and there are only 6 topics that are involved in operation research, which is called OR. So this operation research, the first topic that is covered in operation research is called linear programming. So I'll give a breakdown of the topics covered. So the first one is called linear programming. That is topic 1. Then number 2, we have transportation. Then we also have the other topic, which is called networking. Topic 3, networking. Then we also have the other one, which is called queuing theory. Then we have assignment problems. Then the other one is called simulation. Of course, topic 7 is decision making. This is topic 7. So this is about the topics that are covered in operational research as a full course. So we can now get down to the assignment. Of course, this assignment has the first question. Okay, so question number 1 for this assignment, which is due on the 10th September 2023. And this assignment, question 1, Wadia & Sons Electric Company produces 2 products, batteries and transformers. The products are produced and sold on a weekly basis. The weekly production cannot exceed 25 batteries and 35 transformers due to limited available facilities. The company employs a total of 60 workers, that is on labor force. The batteries require 2 man-hours of labor, while the transformers require 1 man-hour of labor. Then the profit margin per battery is 60, and that of transformer is actually 40. So this is just about this question 1A. Now, the first question says, formulate this problem as an LP that maximizes the profit. Then we're solving this problem using the graphical method. So we can let the number of batteries be represented by X1, because it's the first product. So let these batteries be X1, and let the transformers be X2. So X2, we're talking about, these are transformers. All right, so getting down to this, we can now go to the solution. So in the solution here, we are simply saying that our LP formulation on this one is that we are simply saying we have let X represent the number of batteries and Y represent the number of transformers. So since X1 number of batteries cannot exceed 25 and X2 number of transformers cannot exceed 35. So meaning this is for the batteries. So batteries are represented by X1. And then the other one, we're talking about transformers. So transformers are represented by X2. All right, so this is about what we have concerning this one, getting down to the formulation of an LP problem. So from the question, we are clearly told that the available hours here, we have the total. The company can employ the company employs a total of 60 workers. So the batteries require 2 man weeks of labor. Then the transformers require 1 man week of labor, but the total is 60. So we are simply talking about this one as the one we are looking at. So meaning our objective function is given by Z is equal to 60 X1. X1 is for the batteries, because the profit per battery is 60. So this is for batteries. Then this one is for transformers. So this is what is going on. All right, so getting down to the other one. So from here, we are clearly, you can clearly see that we have the profit per battery is 60, which is for X1. And then this other one, the profit is 40 for X2 for transformers. So from here, we are able to formulate the objective function, where we are simply saying that our Z should be, our Z value, which is objective function, should be equal to Z is equal to, we are going to maximize because we're making a profit, maximize Z, equal to our 60 x1 plus the 40 x2. ST simply means subject to. So subject to, that's the meaning of our ST. Now, subject to, we can get down to this one. Okay, so we are simply now saying subject to. So the one we are looking at, so this is our objective function, 60x1 plus 40x2. This is it. We require from the question, it says, okay, the batteries cannot exceed for 25, and also transformers cannot exceed 35. So they should be less or equal to. So meaning batteries, okay, for batteries on our X1 for batteries. So our batteries will not exceed 25. Transformers not exceed 35, meaning that it will be our X1 for batteries and X2 is for transformers. X1 should be less or equal to 25. Then X2 as well should be less or equal to 35. So this can be constraint 1. So this is constraint 1. This is also constraint 2. So this is about how we are trying to formulate, coming up with the objective function. So actually, this is how this was formulated. Then solving it, so this is constraint 3, coming from the information in the question, that the question is saying that the batteries require 2 man-hours of labor, transformers require 1 man-hour of labor, and the total workforce is 60. So this is about how we got this one. So from here now, we can solve and find how many batteries. From here, we can now find how many batteries and how many transformers. That from the question, we are simply saying we need to formulate and find how many batteries and transformers that we will require to produce in order to maximize our profit. Of course, we know the battery profit is 60, transformer profit is 40. So meaning that our objective function, we need to maximize our Z is equal to the total profit made from the batteries is 60 X1, because X1 is representing the profit from the batteries, and then here to be plus 40 X2 on this is a linear programming topic 1. Subject 2, so this is subject 2. This is our S, subject 2. The constraint, we're simply saying batteries cannot exceed 25, meaning that our X1 should be less or equal to 25, that is constraint 1. Then similarly, our X2 for the transformer should not exceed 35. From the question, there's a 35 that is here. Then constraint 3 is talking about the battery requiring 2 man-hours, so meaning constraint 3, so this is constraint 1, constraint 2, constraint 3 will be that 2x1 plus x2, which will be less or equal to 60 from the man-hours. So this is the total man-hours. So the batteries require 2 man-weeks of labor. Then the transformer require 1 man-week of labor. So this is constraint 3. And this will be bound to now x1, x2, which will be greater or equal to 0, meaning that we need to at least produce a battery and a transformer. So this is how we got this as our LP problem for us to use as we trying to solve. So this is about, from here now, this is on the first one, formulating the LP. LP simply means linear programming. So LP means linear programming or linear program. So linear programming is our LP. And then what next is that we need to solve. Now solving, we need to graphically sort it out. So as we are solving, after coming up with this as our LP formulation, and then since X1 represent batteries cannot exceed 25, and then X2 present transformers that cannot exceed 35. So we have that objective. From there now we can solve. The first one, we cut the X1 at 25, cut X1 at 25 here at this point. So where this one is less or equal to, we shade the other region where it is less or equal to is this side. Then the other one, X2 less or equal to 35, we shade the other one, which is 35 here, we shade it down. And then drawing the constraint 3, as we are drawing it, we have to come up with a table of values. When X1 is 0, X2 will be 60 from here, substituting from this equation. When X2 is 0, our X1 will be 30. And then using these points to draw, so 0,60 is at this point. And then the other one is actually 30,0 is at this point. Shading, we came up with this as the feasible region. So this is the feasible region where all shadings converge. So all shadings come together. So we have all the shadings come together. It is what is called the feasible region. All right, so the corner points, we have this as a corner point of the feasible region, this one as a corner point of the feasible region, this one as a corner point of the feasible region. All right, so this point is 35,0, this is 0,35 actually, so 0,35. That's the point at this one. 25,0, this point is 25,0. Then this is 25 comma 10. And then, of course, we have this point, which is 12.5, comma 35. 12.5, comma 35. So this is just about the corner points of the feasible region. Of course, they can be sorted out simultaneously. So 0.35 is that point. Then we have 25.0, that point. Then we have 12.5, 35, 35, that point. Then we have the other one. Now this one was obtained was just by substituting 35 in this equation. 35 in this equation here, x2 is 35. So we got 12.5. So it's 12.5, 35, that one. Then getting down to the other one, we are substituting 25 in this equation, in the same equation where it's ending up to 60 there. We are getting our x. So x1, 25. So this point is now 25.10. And these are the values we got. The first one is 1,400, substituting the objective function, which was z is equal to 60 x1, then plus 40 x2. So this is about how this one came about. So here we are simply looking at the maximum possible because we are trying to maximize. So meaning that optimal solution is given by x1 should be 12.5 batteries, and then x2 should be 35 transformers, and to give us a maximum profit of 2,150. 2,150. That answers the first part of question 1. The first part of question 1 is cleared. Then from here, we can now look at the, so this one, we have solved the question for 10 marks, the first one. Then we look at part B of question 1, which talks about Konka Advertising Company wishes to plan an advertising campaign for 3 different media, television, radio, and that is different media for the television, radio, and a magazine. This is a part of an advert. The purpose of advertising is to reach as many potential customers as possible. The following are the results of the market study. So television, the radio, and magazine. The cost of an advertising unit, we have these ones. And of course, we have other things. So meaning the print, right? The print media, the print day, prime day, this one can be represented by x1. This one can be represented by x2. This one can be represented by x3. And this one can be represented by x4. Because for the television, we have the prime day and prime time. So you can let them be represented by that. And then you shouldn't spend more than 800,000 on advertising. All right, so meaning that you can formulate the first constraint using that information, at least 2 million exposure. So 2 is a list. So it will be greater or equal to 2 million. 2 is a list. So this one could have this kind of, and then this one should be less or equal to 800,000, well, that's the maximum amount that you have allocated, that you shouldn't exceed that amount. So this is about what we have as constraints. So from here, we can now build up a little bit, getting down to anything else that we need. All right, then. So from here, we can now sort out AOP formulation, the first one says we should actually formulate the AOP for this given problem. So for the 15 marks, so formulate for that part B. So how we formulate is about what we need to do now. The AOP formulation is given by let prime day be x1, let the prime time be x2, the radio be x3, the magazine be x4. So we should maximize z equal to x1 for the prime, for the day, that is prime day. And then this one should be for the prime time. Then this one is for radio. And then the other one represents the magazine. So this is on the way how we are supposed to actually look at this. All right, so then subject 2, we have the 40,000, the first one. So 40,000. So 40,000 x1, x2, x3, x4. So 40,000 x1 plus the other one. So meaning that it should amount to 800,000. So it's just about this that we need to, so 800,000. Then this other one was 2 million at least. So this one was maximum 800,000. This one was the 2 million. The other one has to do with the at least the 3 advertising units. Okay, be bought on prime day. Prime day, we are talking about x1. And so this is the 3, at least the 3 on the prime. Then 2 on the prime time. So this is just the way to go for this. All right, then. So they are denoted by x1 and x2. And then, so here, our LP formulation for this will give us x1, at least for the prime day, at least 3. So 3 is the least for the prime day. Then this other one is the prime time. So this is on the prime time. So this is how this one came. And then this one came from the other information from the question where we talk the number of advertising units on the radio and magazine should each be 5 and 10, should be between 5 and 10, should be between the number of units of number of units of advertising, okay, on the radio and magazine should each be between 5 and 10. So meaning that we are simply saying x3 for the radio, and then the other one is for the magazine, should be between 5 and 10. So this is about how this formulation was obtained for question 1B. Now, question 1C, it has to do with the simplex method, solving using simplex method. Simplex method, I have to explain this method. This is the method that is used when variables are more than 2. So use simplex method for variables that are more than 2. So this is about what the simplex method requires. All right. So getting down to this one, we have the problem here, the question. So we're supposed to sort out this one in simplex because we have variable 1, variable 2, and variable 3. So this sign less or equal to, so there is slack 1. So use slack 1, which is S1. This one also slack 2, which is S2. This one would be slack 3. AC3. All right. When the constraints are less than this or equal to, we use the slacks. So when constraints are less or equal to sign, to write in standard form, only add excuse me, slack variable. So we are simply saying S1 for constraint 1, then S2 for constraint 2, then SA3 for constraint 3. So this is it, what goes on. Writing the problem in standard form. All right, so this is about what we are looking at. In here, we are supposed to write in standard form. So maximize Z, we take all these values the other side. So they are becoming negatives and equal to 0, subject to constraint S1 for constraint 1, constraint 2, and constraint 3. So these are the amounts, the constraint values. So a simplex table, you go for the basis. In a constraint 1, there is no Z, 0. Coefficient here for X is 2, for Y is 3. For Z here, there's no Z, it's 0. S1 is 1 coefficient. Slack 2 is 0. Slack 3, there's nothing there in constraint 1. And right-hand side, this one is called right-hand side. So right-hand side. So this is about how we are getting to this. And then constraint 2, similarly, it's S2, 0, Z there, 0. The X is 2, the Y is 0, the Z coefficient is 5, the S1 coefficient is 0, S2 is 1, S3 is 0, right-hand side is 10, S3, we have 0 Z, X is 3, Y is 2, Z is 4. The slacks S1, S2 are zeros, and S3 is 1. Right-hand side is 15. Then the Z row, we have 1 coefficient. The X value coefficient is -3, -5, -4. The slacks are zeros up to the right-hand side. So we have to select the most negative. Most negative is -5. So our most negative, we are simply saying is equal to -5. Then find the ratio for the most negative values. Find the ratio for most negative. So here the ratio 3 into 8, 8/3. So 8/3 is the same as 2.67. So this is a 2.67. Then this is 15 divided by 2 is 7.5. Do not find the ratio for 0. Do not find the ratio for 0. Do not find ratio for 0. What I mean is that we don't have to find the ratio for 0 here. That's why it's a dash. So meaning that the smaller ratio is the smaller ratio is actually giving us the 2.67. So meaning that Y will actually displace S1 from the basis, select the smaller ratio. So Y is going to occupy all variables that S1 was occupying. And S1 is a basic variable because the basic variable is a variable that has a 1 on its position in the column and the rest are zeros. So basic variable is a variable. So basic variable is the variable that has only a 1 on its position in the column and the rest are zeros. So that is about what a basic variable is. So it's a variable that has a 1 on its position and the rest are zeros. Okay. So what I'm simply saying is what we are simply saying is that we need to y1 is coming here and the rest in this column should be zeros. So we're going to use the same equation, the same variable for y. So simplex table 2. So what here it should have a 1. When this one comes here as a y will displace, y displaces S1. So S1 displaces S1. So what we are simply saying, this y is going to get all the values that S1 was occupying, but here you should have a 1. So we divide 3 by each of these variables so that we make this one a 1. So it's a 1 now. So we can use it to reduce this one to 0 because it will come here. So on the position should be a 1 here. And then the rest in this column should be zeros. So meaning that we are making this a 1. Then this one is already a 0, which is okay. Then we can multiply by -2, the same one, this one by -2. Then whatever we get, we should add row 3 so that we reduce it to 0 on this point. We need a 0 there. We're simply saying that there we need a 0. All right. So here we are simply saying that on this point we need a 0. How do we get a 0? We need to actually multiply by -2 throughout. So this by that, this by that, this one by that, this one by that, this one by that throughout. Then what happens? We add row 3 because we need the 0 there. So as we add, this one is giving us 0. This one adding, so it's given us 5/3. This one has given us a 0. This one has given us a 4. This one giving us -2/3. This one is 0. This one is 1. This one is 29/3. This is new row 3, which is equal to our AC3 as we prepare simplex table 2. Okay, then we need the 0 in the Z as well. So meaning that multiply by +5, you multiply it by what we made as a pivot row. This Y will substitute S1 because the smaller number is 3. So this one is our pivot row. So our pivot row. So this row, it becomes our constant. So it becomes our constant to reduce other rows as reduction matrix becomes constant to reduce other rows. So this is about what we have. So meaning that 5 by that, so 5 by 0, 5 by this, so this is Y. The one this equation, this one is for Y. So multiply each of these by what we having here. Then after that, we are adding. So we're getting 1. So this solution is not yet optimal because we have negative. This is a new Z because we needed a 0 here. Where there's 5, we have reduced to 0. This one has been reduced to 0 using the pivot row. It has been reduced to 0. So this is about what we know and what we have. From here now, simplex table 2 came in, which is this one from the reduction. So this is a Y which displaced. Initially, we had S1 here. So we are still have a problem. We still have a negative. As we optimize in the Z row, optimize the Z row should not have a negative. So optimize Z row should not have a negative. So this is according to the optimization. So Z row should not have any negative as we are optimizing. So it's also not optimal. So here we need to find the ratio. Here is a 0. So don't find the ratio there. Here we are getting a 2. Here we are getting 2.47. So this is a smaller. The number to give us the smallest ratio is called entering element. Number to give a smaller ratio. So number to give molar ratio is called entering element. Okay, so this one is called entering element. Okay, so now you have that one, so we reduce it, divide it one by, so this one becomes our Z, not the Z like a Z row, it becomes our Z, this one, because it has removed this one, so there will be a Z as we prepare the simplex table 3. So you use it to reduce other rows. So this one is already 0, so we can just reduce this one and this one. So we have this one multiplied by -4, then add row 3. So our new row 3, which is still our AC3, became, after multiplying this by that, 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 we added to each of these ones. We are getting the values which are here. So this is new row 3, which is AC3. We have to reduce the value in Z now using the same. This one is our pivot row. This one is our pivot row. So this pivot row, we are now sorting it out, multiplying by +4 to each of these, to the Z, to get these values. After adding, we are getting the values in the, so this is new Z, new row Z. Okay, so after this new row Z, this solution is optimal because all values are positive. All values are positive. So here we have solution optimal. So our solution is optimal because all values are positive in the Z row. So this is just about what we have concerning this question. So preparing our y is still the same, this one, because it was already 0. This one we changed to a 1. So y, it has a 1 here, the rest are zeros in this column. It's a basic variable. S2 is a basic variable because it has a 1, the rest are zeros in that column. S3 is a basic variable because it has a 1 on its position, and the rest are zeros. So this is a matrix. 1 0 0 0 1 0 0 is a reduction, matrix reduction. Using linear programming, we are looking at matrix reduction in this kind of program. So using LP. LP simply means linear programming. All right, so the solution optimal is given by y is equal to 8/3, z is equal to 2, S3 5/3, and z is equal to this. So this is optimal solution. Y is 8/3, z is 2, and S3 is 5/3, x is 0 because it's not here. So we have this and that. X is not here, so it's 0. Proving this, we obtain the objective function is given by this one. So we can substitute there in that equation. to get what we need concerning this kind of equation. From here, you're substituting in this as our objective function. OB means objective function. Objective function. So this is what is going on in this kind of question. So now proving this, we are simply now saying that substituting x0 here from this y is 8/3, oz is 2, so this is 8, then 40/3. Then here we have a 0. So it's giving us 64/3. 64/3. This is what we have as the solution concerning this kind of program. So this is on this question concerning question 1. All right, question 1A. So we'll build up a little bit, getting down to the other question, which is question 2 of this problem in a little bit, but not now. We'll get down to question 2 in the next lesson, the next class. For now, we are to formulate the NLP problem for question 2 and what is the primal problem and the dual problem. So in linear programming, we have primal problem. This one is called original problem. Original problem, or in short, the initial problem. Initial problem. Then we have the other one, which is the dual problem. Dual problem comes from primal problem. So the dual, if primal problem is maximization, dual problem, the dual problem will be minimization. So this is what happens here, and we can end the class for now. So of course, the dual problem is denoted by W. All right, so get deeper in how we formulate the dual and how we sort out the dual problem using the original primal problem. So we can end the class for now. The other ones will be resolved, other questions will be resolved in other classes question 2 of this assignment we resolved in the other class. So this is just about where we are ending now. All right.